Mm, Good morning and assalamu alaikum. So I'm back with another video, and this time we are going to solve a paper for O-level physics. And as you can see on the screen, this is a paper 2, which is a theory paper, which has a total number of 75 marks available, and you have 1 hour and 45 minutes to do it. So this paper is from May-June 2019, and this is variant 2 of paper 2. So we'll get started. We'll write our candidate name, candidate number, and then we'll get going. Okay, so obviously you know the paper format. Section A contains 45 marks, and you have to do all the questions from this section. So I'm going to start with section A. Question number 1 reads, a student records the mass and volume of two irregular objects, one made of iron and the other made of copper. Okay, so one of the objects is made of iron and the other is made of copper, and this is the equipment that the student is using. So there is a mass balance, and he will place his object on the mass balance that will give him the mass in grams. And then there is a measuring cylinder, which he'll use to measure the volume. He'll use the displacement method where he'll have just the water in the cylinder first, and then he'll have his rock, and then the water rises, and he can subtract the two values to calculate the volume. Okay, so part A reads, describe how to determine the volume of an irregular object with measuring cylinder. Okay, so as we just discussed above, we use the displacement method. So first you'll have your measuring cylinder with just the water filled halfway through, and you don't want to fill the cylinder all the way to the top. You need to leave some space for the water to rise, and then you take the reading, and let's call it V1. So we take that reading and we call this V1, and then we put this rock, and we'll see the water level rising. So let's say it rises to 70, and let's call this V2. And then what we are going to do is subtract the two values, the final one with the initial one, and this will give you the volume for the rock. So in our case, if it was 70 and the initial was 40, our volume would be 30 cm cube. So how would you write this answer? So there are basically just two steps, and the first one would be fill the measuring cylinder with just water. Take the initial reading as V1, then place the object inside the cylinder, take the new reading as V2, the volume will be V2 minus V1. So we haven't left any room for any ambiguity here. We have given a proper complete answer here. Now how do you calculate the density of iron? Okay, so for iron, if you can see on the table, we have the mass available and we have the volume available. So all we need to do is just use the formula. Density is mass over volume. So mass of iron is 400 grams and volume is 51 cm cube, and our density would be 400 divided by 51. So on the calculator it says 7.84 4, 3, and so on. But you can't write your answer like this. You always have to round it off to a suitable number of significant figures. So in this case, we can write it as 7.8, or you can write it to 3 significant figures, 7.84. Now you don't forget the units. Units for the mass were grams, and for volume were cm cube. So density, the unit would be gram per cm cube. Moving on to the next part, a third object which is also made of copper. So the third object is also made of copper. This information is vital here. You need to read the question carefully. And there's another important piece of information. It has the same volume as the iron object. So the material is copper, but the volume is the same as iron object. Calculate the mass of this copper object. Okay, so again we use the same formula. Density is equals to mass over volume. So if you want to calculate the mass, that would be density multiplied by volume. Now because it is made of copper, its density would be the same as the density of copper. We haven't yet calculated the density of copper, so let's go and calculate the density of copper first. Density of copper would be 350, which is the mass, and divided by 39. So 350 divided by 39. This would give me the density of copper. 8.974. Now notice I'm going to use this exact value here, or I'm going to use the answer option, answer button in my calculator, because I don't want to round this off, round this value off during my calculations. You always round off your answer at the end when you have to write your answer in the answer space, because this is not your final answer. You have to use this calculation further, so it's best not to round it off right now. So the other important piece of information is the volume of the object. Now remember, they have written it that the volume is the same as the iron object. So the volume of the iron object was 51, if you can see here. So what you're going to do is to calculate the mass of the object. You write the density as 8.974. Whatever the answer is, just use the answer button from your calculator and use the volume of the object which was made of iron, which was 51. So mass would be 457.692 and so on. Now again you want to round this value off. So again 3 significant figures is really suitable, just go with it. 458. So I have rounded it off. Now you don't forget your units. Remember, the density was in gram per cm cube and the volume was in cm cube, so your mass would be in grams. There you go. Now state and explain what happens to the density of the iron object when it is heated. Now remember, whenever you heat any object, it's going to expand. So if something expands, it means the volume is increasing. And if the volume is increasing, if you look at the formula for density, density is mass over volume. Now if you look at this, if the volume of the denominator is going to increase, it means that the density of the object is going to go down. So volume and density are inversely proportional to each other, kind of. So look at the command words carefully. State, they want you to state what will happen. The density will decrease. So I'm stating my answer first. The density will decrease. But this is not enough. We have to explain it as well. So why would that happen? Because the object will expand, which will increase its volume. Alright, so this is the first question. Now let's go to the next one. Okay, so on to question number 2. Here we have a manometer, and as you know, the manometer tells you the difference in pressure on the two sides of the meter rule. So we have a U-tube. On one side we have a container of gas which is connected to it, and the other side is exposed to the atmosphere. So the gas contains in the container exerts a pressure. Define the term pressure. Now you should always learn your definitions, you should always memorize them. And pressure is just force per unit area. That's it. And you can also write if the formula of a term is its definition, which is sometime it is in physics, for example with work and with moment and with pressure. These are quantities where you can write the formula as a definition as well. So you can write the formula as well, but always remember to write the formula in words and not in just symbols. If you're writing just the symbols and not explaining what the symbols mean, you're not going to get the marks. So if you want to write the formula, then use complete words. Force upon area, that will give you your mark. Now the density of mercury is 1.4. So what happens is I always underline my important information while reading the question, because this will always help you not miss out on anything important, any important detail which is written in the question. Gravitational field strength is 10 on earth, and the pressure of atmosphere is 1 into 10 to the power 5 Pascal. Calculate the pressure of the gas in the container. Now remember, they are telling you to remember pressure, to calculate the pressure of the gas and not just the pressure difference. Remember, this is a manometer, so by itself it's not going to give you the directly the pressure of the gas. It's only going to give you the difference in pressure. So you know you have to see the height difference from the meter rule, and that height difference is, I think from there we can read it as 16. I would go with 16, and from here we can read it as 0. So from 0 to 16 our height difference is 16 centimeters. Why I'm saying centimeters? Because it's mentioned on my instrument. So always don't forget your units at all. So here we have formula for difference in pressure. Now remember, we are just calculating the difference in pressure between the atmosphere and between the gas pressure, and then we are going to calculate the pressure of the gas. So the formula is rho g delta h. Rho is the density of mercury, which is 1.4 into 10 to the power 4. Then we have the value of g, which is 10, and then we have the height difference. But remember, the height difference is given in centimeters, and I want to calculate the pressure in my SI units, and all other quantities are in SI units. Remember, the density of mercury is also in kg per meter cube, so I need to convert it to meters. So 16 centimeters, if you divide it by 100, you get 0.16 meters. So that's what I'm going to use, 0.16. So converting my units, I'm going to calculate the pressure difference. So 1.4 10 to the power 4 multiplied by 10 multiplied by 0.16. That will give me the pressure difference, 22400. So this is pressure difference between the gas and the atmosphere. But let's figure out which of them is applying more pressure. Now is the gas applying more pressure than the atmosphere or less pressure than the atmosphere? From the diagram you can see that the atmosphere is pushing the mercury down much more compared to the gas. So pressure of atmosphere is much more on the left hand side than the pressure of the gas. So what we have to do is, if the difference in pressure is this much, then all you have to do is subtract this value from the atmospheric pressure and you will get the pressure of the gas. So pressure of the gas will be pressure of the atmosphere minus the pressure difference. So pressure of the gas would be 1.0 into 10 to the power 5 minus our answer, which was 22400, and that will give me my pressure of the gas. which is turning out to be 77600. Now this is correct to three significant figures, so I can write it as it is, or I can write it in standard form. That would be 7.76 into 10 to the power 4. But don't forget your units. The units will be pascals. If you forget the units, you won't get the last marks, which is for your answer. Part C. On figure 2.1, the level of mercury on the left hand side is lower than on the right hand side. Obviously we can see that left hand side is lower than the right hand side of the mercury. The gas inside the container is heated now. So on the right hand side, the gas chamber is heated, which will obviously cause the temperature of the gas to increase. This causes mercury levels on both sides to be the same now. So determine the level of mercury as shown on the ruler when this happens. So they're saying that you heat this one, you apply heat to it, and because now gas is going to apply more pressure now, so this pressure will become the same as the atmospheric pressure. So where would the mercury go to? Obviously the amount of mercury inside the tube is not changing, so the mercury that will drop on this side because of the pressure being applied to it is the same amount of mercury that will rise on this side. So the total difference between these two heights was 16 centimeters. So if they're going to come to the same level, this will have to drop down by 8 centimeters, and obviously this will have to go up by 8 centimeters. So they will both end up at 8, which is right about here. So this will reach here and this will reach here, and then the levels on both sides would be the same. So that answer would be 8 centimeter. Again, do not forget to mention your units. Explain in terms of gas molecules. Again, now they want you to describe what is happening to the gas molecules in order to give your explanation. Read the question carefully. What causes the level of mercury to become the same? So basically they're asking you, why is the level dropping here and why is the level increasing here? So simple explanation for this is, because the gas pressure gets the gas gets heated, the molecules inside the gas are now going to move much faster, and we know that the pressure applied by the gas is because of the collisions of the molecule, right? Collisions of the molecule with the boundary or anything that is in contact with it. So because heat is supplied to the gas, that heat converts into the kinetic energy of the molecules and they move faster. Therefore the pressure applied by the gas increases. Now the pressure on the mercury increases, obviously is going to be pushed down, and from this side the mercury is going to rise. So this is our answer, and we are going to, obviously you have to write an answer in paragraph forms, but do not forget your important points. You're not going to write your answer as in bullet form. Write it as a paragraph, but in your head you should have all the 3 points. Remember, we have 3 marks here, so to get 3 marks you need to give 3 valid points, a proper explanation in the right order. So molecules of gas gain kinetic energy. Because their temperature is increasing, they're going to get kinetic energy, they're going to gain kinetic energy. They are moving faster, so they will exert a larger force and hence larger pressure on what? On the mercury column. On the mercury column. So it will be pushed down from the right. But remember, this word is also very key. The word same. Why would the level be the same? Remember, the manometer gives you the difference in pressure. So the level would be the same because the pressure of the gas eventually becomes equal to atmospheric pressure. And there is your complete answer. Okay, let's move on to the next question. Okay, so we're going to continue with question number 3, and it reads it's showing you basically 3 rays which are traveling from point S inside the water to the air. So they are crossing the boundary between water and air, and you can see the first ray is getting refracted and moving away from the normal, because as we know, if the ray of light goes from an optically denser medium to an optically less dense medium, like for example from glass to air, or in this case from water to air, they are going to move away from the normal. The angle of refraction would be larger than the angle of incidence. The second one is then also refracting, but it goes right along the boundary between the air and water. So in this case, the refraction is so large that that your angle of refraction is basically 90 degrees. And in the third case, the beam is just reflecting back. So that's the case of total internal reflection. So on part A says, on figure 3.1, mark the critical angle and label it C. Obviously, by the definition of critical angle, you know it's that angle of incidence when the angle of refraction becomes 90 degrees. So we can see here the angle of refraction is 34 degrees. So here our angle of incidence would not be a critical angle. In the third diagram, the third beam, its total internal reflection, the refraction is not even taking place. But in the second diagram, your angle of refraction is 90. So your answer would be this. The angle of incidence will now be known as the critical angle. And remember, you can't give this as your answer or the other angle 90 degrees as your answer, because that would be wrong. The angle of incidence or refraction, any angle in this chapter, is always going to be calculated between the beam and the normal and not the boundary itself. So the angle drawn in red and labeled C is your answer. Okay, state why only one of the 3 rays is totally internally reflected. They're saying why only one, and why not all the others? Because for total internal reflection, you want your angle of incidence to be larger than the critical angle. If angle of incidence is larger than critical angle, only then is the ray going to totally internally reflect. Otherwise, it's just going to be simple refraction. Because only in the third ray or you can say the one at the right, you can just mention, you can always refer to your diagrams in the question, because only in the third ray is the angle of incidence greater than angle of than the critical angle, sorry. So angle of incidence need to be this condition has to be fulfilled, otherwise it's just going to be simple refraction. Okay, calculate the refractive index of water. Now this one is a little tricky. It looks simple, but you can easily make a mistake. You know, you might have seen this formula in your books or in your notes. to calculate the refractive index. Now if you look at it, our angle of incidence here is this one, 25, and angle of refraction is 34. But the problem with this is that it's going to give you an answer which is completely wrong, because remember, for any object, the angle for any object other than vacuum or air, the refractive index is always going to be greater than 1. So if for some reason your answer is less than 1, just remember that that answer is wrong. For refractive index, the answer is always going to be greater than 1. So in this case, where the light is traveling from the angle of incidence from water to air, from a denser medium to less dense air, always use the bigger angle. If you just remember to use the larger angle on the numerator, you're always going to get the right answer. So I'm just going to use the reciprocal of this formula, where the angle of refraction would be at the top. So that would be sine 34 divided by sine 25, and that would give me an answer of, let's check. Remember to keep your calculator in degree mode, because the angle is given in degrees. If it's in radians, then you would get the wrong answer. And the answer that we get is 1.3, which is absolutely correct. And there are no units for refractive index, because it's just a ratio. So whenever you have a ratio in physics, it never has a unit. The critical angle, so the formula for critical angle is pretty simple. Sine c is equals to 1 over n, and I have already calculated n. So what I'm going to do is c sine inverse 1 over 1.3, and that should give me an answer. And the answer turns out to be 49.09 degrees, but always round off your answer to 3 significant figures, so that would be 49.1 degrees. So that is that. Now we'll move on to question number 4. Okay, so we are on to question number 4 now, and it's basically saying that a star emits electromagnetic radiation. We know that star emits light, and light is just a part of electromagnetic radiation. So the stars or the sun don't just emit visible light, they emit all sorts of electromagnetic radiations in a range of wavelengths or frequencies, and it's only the light that we are able to see with our eyes. So they're saying that the brightness of each form of radiation is shown on the y-axis, and the wavelength is basically giving the range of wavelengths of that electromagnetic radiation which is coming from the star. So they're saying that the radiation from the star is brightest at one wavelength, and we can see so what is that one wavelength in part A? So we can see this is the highest point on the graph easily, which is very easily watchable. So you can just see the wavelength at which the brightness is highest, and just read this value from the graph. So that would be 1.2. That would be 1.2 into 10 to the power minus 6, and don't forget your unit. The unit is meters. It's given in the graph. So that is your wavelength, visible light. Part B, visible light has a wavelength between this value and this value, and what they're saying is the radiation in A lies just outside the visible part of the spectrum. So it's just outside the visible part of the spectrum, and this is the range for the visible part, this one right here. So they're saying state the name of the region of that spectrum that contains the radiation in A. Now in order to solve this one, you need a bit of memory. Obviously you have to memorize, you should know this, that you need to be able to memorize at least the order, if not the powers of tens or the order of magnitudes. You should still be able to remember the orders in which in the order of increasing wavelength or in the order of increasing frequency, all the constituents of the electromagnetic spectrum. So in this case we have visible light, and if you remember, around this visible light, one of the parts is red and one of the parts is completely blue, or you can say violet. So one of the parts is violet, one part of the spectrum is violet and one part of the spectrum is red. So the very easy thing to remember here is that the part which is alongside the red region is called infrared, because it has the word red in it, and it's just a little trick that you can use. And because this part is violet, the part alongside this one will be known as ultraviolet. And this part of the spectrum that I have drawn, or the way I have drawn it, is going to show you the increasing wavelengths. The wavelength is increasing in this direction. So if you see the graph, our wavelengths are of the magnitude of 10 to the power 6. We have this value given here, and the visible light region has the power 10 to the power minus 7. So if you understand standard form, you know that 10 to the power minus 6 is definitely greater than 10 to the power minus 7. So our wavelengths on the graph are basically bigger than the visible light region, so they are definitely infrared. So our answer would be infrared. Now you could have just answered it in 1 second if you remember it, but you still have to be attentive about reading the power, the order of magnitude from the graph and everything. And if you just remember the whole spectrum, then it's very easy to answer. It's just your memory. Now determine the frequency of radiation in part A. Okay, so in part A the wavelength was this, so you have to use your answer from this point, and the speed of light is given. Now this thing, the speed of light, sometimes they are not going to give this to you because they expect you to remember the speed of light. And even if it's infrared waves or ultraviolet waves or any other sort of wave, gamma rays or x-ray, you need to remember that all the electromagnetic waves travel at this speed, the speed of light. Okay, so the equation is very simple. V is equals to lambda f, and what we have to calculate here is the frequency. So frequency will be V over lambda, and if V is 3.0 into 10 to the power 8 and lambda is calculated in part A, which was 1.2 into 10 to the power minus 6, we can get our frequency. So let's calculate this one. So the frequency turns out to be 2.5 into 10 to the power 14, and don't forget the unit of frequency, which is hertz. Okay, so we are done with question number 4 as well. Now we'll move on to question number 5. So on to question number 5. This is from static electricity, and what they have basically given you, they're referring to this left equipment as the dome, but actually this is known as a Van de Graaff generator, and they're referring to this one as the ball. So make sure in your answer as well you refer to them and with the same words as they have used in the question, otherwise there will be just confusion. So use the word dome for this one and use the word ball for this one. Now they're saying before the machine is switched on the left hand side you have a machine, and before the machine is switched on the metal dome, both of them, the metal dome and the ball, are uncharged. Okay, and when the machine is switched on, the metal dome becomes negatively charged. Explain how charging the dome causes the metal ball P to become positively charged. So we know in the end P is going to become positively charged. So why does that happen? That's what they want you to tell them, and they have 2 marks for this one. So what will happen is when the machine is switched on, the dome is negatively charged, and that part we don't have to explain, although they can ask for an explanation for this as well. But let's focus on the question on right now. So if this dome is negative, obviously the electrons in the metal ball are going to be repelled because electrons have negative charge. So any electron inside P will be repelled. It will go to this side. Okay, and it just wants to go as far away from the dome as possible. Now you're not going to mention positive because positive charges are because of protons, and protons are inside the nucleus. The protons in a material are not going to move. Positive charge does not move. It's only the negative charged, the electrons, that can move within a conductor. So never make the mistake of saying that the positive charge is attracted to the dome. So what you're going to do is you're going to say the negatively charged electrons are repelled. This is 1 mark. You don't have to mention the obvious things which are already written in the question, and you're just going to waste your time and your space. So the dome is negatively charged. You don't have to mention it again in your answer. It's already written there. It's already shown on the diagram. They already know it. Now what are the electrons going to do? Look at this. The rod is conducting, so this rod is also a conductor, means electrons can actually move through the conductor. Why would they want to move through the conductor? Because they want to get as far away as possible from this metal dome. They are negatively charged dome, they are being repelled. And because the conducting rod is connected to the earth, it's a sea of electrons, or it's a sink of electrons. It's always going to accept electrons. So the electrons will move to the earth. Now since the electrons have left the metal ball, it has a deficiency of electron. So the ball has a deficiency of electrons, which means there is more positive charge on it than negative charge. So overall it has a positive charge. So it will be left positively charged. Here's your complete explanation. Basically it's just 2 points. The first point is this one, that will give you your first mark, and then this whole sentence is your second point. Basically because the electrons are being repelled, they're going to go to the earth. But why is this positively charged? Because there is a deficiency of electrons, so you have to mention that. Now they have a photocopier. Now in the part where we studied about the applications of electrostatics, photocopier was one of them, and there was a whole process of how it works. If you remember the whole process, then there wouldn't be any issue. But what happens is, even if you forget the whole order, or if you don't remember it step by step what happens, but you have a basic understanding of how electrostatics work, or how a basic machine works, or what a photocopier is supposed to do, you can just order these in the right order. So basically they have given you the steps of how a photocopier works, but they're all in the wrong order except the first one and the last one. So A and F are basically out of the equation. They are already taken out of the equation. They are in the right spot. Now we have to decide for the 4 steps in between where they are going to go and pick them in the right order. So just by using a simple understanding of what a photocopier is supposed to do, it's obviously going to make the image the last step. So you cannot choose step D. Just be careful, step D or anything. So step D cannot be the last one, because the first part of the of a photocopier is where you actually use the original image to project it, or you place it on the screen, and then it is projected onto the drum. So the first one is going to be the first step when you use a photocopier is to place your original paper on the photocopier. So that is option D. An image is of the original page is projected onto the drum. So this is literally common sense. You don't really need any physics understanding to do this one. So D is out of the equation now. We are done with D. Now what happens to the drum and why is it going to make an image? So the thing is, the drum cannot transfer the powder directly right now, or it's not going to attract any powder right now. The thing is, the drum was positively charged in the beginning. The drum is given a positive charge, so the whole of the drum was given a positive charge, and then we projected the image onto the drum. But then what happened was, because our image was there and the light, the green light which comes on from the bottom onto our image, from the white parts of the paper, the light is reflected back onto the drum, but where the black parts of the image are there, where there is ink on our original image, it is not reflected back onto the drum, and this is the part where the drum is basically remains positive charge, and where the light actually hits the drum from the white parts, the charge leaks away. So what happens is, this is going to be part C and this is going to be here. Part C is going to be done here, so we're done with that as well. Now the drum rolls against a piece of paper, transferring powder to the paper, and the positively charged parts of the drum attract a black powder. Obviously you can't transfer the powder to the paper before the drum attracts it. The drum has to attract the powder first, and then obviously it has to transfer it to the paper. So that is again common sense. So the positively charged parts of the drum attract the black powder. So this is B, and then you have part E. So just a little memorization of how it works. You're going to project your original image onto the drum. So this is so you place your paper onto the drum, and what happens is, on your original image some parts are colored or they are darker in color, and because the page is white, some parts are very bright. Now the bright parts reflect the light very well, and the darker parts absorb the light. So when the light is shown onto that original on the original page, the white parts reflected very well back onto the drum, and those parts where the charge leaks away, the positively charged drum is basically neutral now, but the parts of the page which did not reflect any light, so that those shapes on the drums or those specific parts of the drum will still be positively charged, and they are going to attract the black powder. So now the powder is stuck onto the drum, and then a new page is going to be pressed against the drum, and it's going to be heated. So what happens is, the new page rolls against the drum, and the powder which is stuck on the drum is transferred onto the paper. So the new paper will now have the exact image which you had in your original image as well. So this is your answer. Now in order to get two complete marks, you have to get all of them right, and in order to get at least 1 mark, you need to get at least part C and part D right, otherwise you're not going to get any mark in this one. Okay, so we are going to move to question number 6 now. So starting with question number 6, this is definitely from DC circuits. You have a circuit in front of you where the EMF of the battery is 6 volts, and you have an ammeter which is going to measure the current in the main branch. So it's going to measure the current of the whole circuit, the total current which is going to pass through P plus Q, and they have given you the resistances of the lamp. So lamp P is 15 ohms, and the ammeter reading, the current which is passing in this branch is 0.65 amperes. So we don't know the resistance of lamp Q right now. Now they want you to calculate the current in lamp P. Obviously lamp P and lamp Q are connected in parallel, so they are both going to have the equal potential difference across them, and you can see that lamp P is connected to the positive terminal and the negative terminal of the battery. So the potential difference across P is the same as the EMF of the battery. So V is equals to IR is the equation that you're going to use. Potential difference is 6, current is what you have to calculate, and the resistance of P is 15 ohms. So I, according to our calculations, would be 6 divided by 15, and you get 0.4 amperes. So 0.40 amperes should be your answer. Calculate the resistance of the lamp Q now. So obviously, if 0.4 amperes of current have gone to this branch, so the remaining current definitely would have gone to this branch. So let's calculate this one first. What is the current through lamp Q? And that can be calculated by subtracting the current of lamp P from the total current. So 0.65 minus 0.40, and that will give you 0.25 amperes. So now we know that 0.25 ampere of current is passing through Q, and we know that the potential difference across it is also 6, same as P, because they are in parallel. So we know the potential difference and we know the current. All we need to do is calculate the resistance. So resistance is going to be 24 ohms. Don't forget the units. Sorry, 24. It's going to be 24. The two lamps are now connected in series to the ammeter and the same battery. In the space below, draw the diagram. So the battery is the same, but now the two lamps are not connected in parallel, they are connected in series with each other. So they want you to draw the diagram for this one. And series and parallel is pretty simple. So first we'll draw lamps P and Q, and now they are in series and not parallel. And the ammeter obviously is also going to be in series. This is our battery. So let's make sure we do our battery properly. I made a mistake, I just drew a cell. Remember, the battery is more than one cell in series. This is our battery, and this is your circuit, lamp P and lamp Q. Simple enough. Last part, explain why the ammeter reading is less than 0.65. Okay, so why is it less than 0.65 amperes when the lamps are connected in series? Obviously, when you connect them in series, you calculate the resistance as such, R1 plus R2. But when you connect them in parallel, you calculate the resistance like this. And you can clearly see from the equation that when the lamps are connected in parallel, their combined resistance will be less than the smallest lamp out there. But if they are connected in series, the combined resistance will be larger than the individual resistances. So the resistance is going to be increased, and more resistance means less current. So it's a pretty simple answer. In series, the resistance is larger than in parallel, so the current is going to decrease. Simple. Let's move on to the next question. So question number 7, we have a U-shaped, a horse-shaped magnet, and we have a copper wire which is placed on top of two other copper horizontal rods. And if you can see, the copper wire is basically free to move, the black one, and it can basically roll back and forth on this copper wire if a force is acting on it. And the copper rods are connected to the battery, and they're saying that the crocodile clip A, which is right now not touching the terminal, so now it touches the positive terminal of the battery, and this causes the copper wire to move. And this copper wire, when it's going to move, obviously it's going to depend, the direction is going to depend on the direction of the force. So they're saying on figure 7.1, mark with an arrow the direction of the current in the copper wire. So the direction of conventional, when they're talking about current, we are always talking about conventional current, which is from positive to negative. So current is going to go like this. They're saying mark with an arrow the direction of the current in the copper wire. So in the copper wire, the current is going to be like this, in this direction. Okay, so we know the direction of the current now. Part B says explain why the copper wire moves along the copper rods. Now obviously we have a wire in which a current is passing, and that wire is placed between the magnet. So this is an electromagnetic effect which is going to take place. But why does that happen? Well, because when the current is passing through the wire, it's basically a magnet itself. It acts as an electromagnet, a temporary magnet. And because there is a current in the wire, it's going to create its own magnetic field around the wire. That magnetic field is going to interact with the magnetic field of the permanent magnet which is around the wire, and because of that a force will be applied on the copper wire. So you're going to say there is a magnetic field due to current in copper wire. That's the first part of your answer. This field will interact with the field of permanent magnet. This will cause a force on the copper wire, which is why it's going to move. Name two different devices that use this effect. Now one is pretty obvious. The DC motor definitely uses this effect, where we have a whole coil of wire and basically multiple coils of wire, and they are placed between a permanent magnet, and when the current passes through the wire, the coil rotates, and that's when we have a DC motor. But this effect is also used in loudspeakers, where you have alternating current passing through a wire, passing through a coil, and because there is an alternating current, there is a force back and forth on the wire from a nearby permanent magnet, and that's when the coil vibrates and the cone on the loudspeaker vibrates, and then it creates a sound because of the vibration. But you can write any other instrument as well, or any other piece of equipment which uses these two equipment. So for example, your fan on the ceiling uses a DC motor, so you can basically write a fan, or you can just write a speaker, or your telephone, or your television, because it has a speaker, so you're going to say that it uses this effect to its advantage. Okay, on to the next question. Now here we have a CRO, a cathode ray oscilloscope, and the device is used to show a force on an electron in an electric field. So they want to show electron, in which direction would there be a force on the electron if it passes through an electric field. Part A says explain how a continuous flow of electrons from the filament is produced in this apparatus. So they want you to tell why the electrons are emitted in the first place, and then why is there a continuous flow of electron from the filament. Well, we know, we have studied this, and it's just 2 points. Heat in the filament will cause thermionic emission. Thermionic emission is the emission of electrons from any metal when it's heated to very extreme temperatures. So this is the first part of your answer. And then why is there a continuous flow? So if you look at the diagram carefully, if electrons are emitted from the filament, they need to be able to travel continuously from this direction. So they have another measure in place, and that is an anode. So anode is positively charged. So if this is positively charged, it's going to attract the electrons towards itself, And remember, there is a very large potential difference between the anode and the filament. Filament is basically negatively charged here, and what happens is the positively charged anode is going to attract all the electrons towards it, so it causes a continuous flow of electrons in that direction to the right. So the positively charged anode attracts the electrons. So these two things together produce a continuous flow of electrons. Part B says when an electron in an electric field is placed, there is a force on the electron, but the direction of this force is in the opposite to the electric field. So why does that happen? So what they're saying is, if you have a metal plate and it's positively charged and a metal plate which is negatively charged, there is an electric field between it. If an electron passes through this field, the force that it's going to experience is going to be opposite to the electric field. So first of all, you need to remember what do you consider as the direction of the electric field. The direction of the electric field is always from positive to negative. So the electric field lines are basically facing downwards, and we know when the electron passes through this field, it's going to be attracted upwards. Why? Because electron is negatively charged and it's going to be attracted by the positively charged plate and repelled by the negatively charged plate. So they're saying describe how the metal plates can be used to show this. So obviously, first of all, you want to charge the plates somehow. So what you do is you connect a battery across the two plates, across the two terminals of the plates, and obviously one of the terminals, the negative terminal, can be connected to the bottom one, and the positive terminal can be connected to the top one. So now the top plate is positively charged and the bottom plate is negatively charged. Now when our electrons are going to pass through the plate, we can clearly see that they are going to be attracted upwards, and that's all we have to mention. That's all we have to mention. So connect the terminals of the plates to a battery. And because the electron is negatively charged, we will be able to see the electron being deflected towards the positive plate. And that's your answer. So I think we are done with section A. Now this is 45 marks out of 75. Now we're going to start with section B. So section B consists of 3 questions. Each of them have 15 marks, so that's 45 marks in total, but you don't have to attempt all 3 of them. You can attempt any 2 questions out of 3, but since I'm solving this for YouTube, I'm going to solve all 3 questions here. So let's go through each of them one by one. Okay, figure 9.1 shows a map of a route taken by a car as it travels from A to B. So there's a car from town A to town B and is taking a weird path between 2 points, and what they're saying, the journey involves a distance and a displacement, and what they want us to do is calculate the displacement from A to B using the scale on figure 9.1. So what I would do here is look at the diagram carefully, and they're saying that one side of the square is equal to 5 kilometers. Now the displacement, first of all, that you need to understand is the displacement is distance in a straight line, the shortest distance in a straight line between 2 points. So this is going to be your displacement. So if you draw that what you have is basically a right angle triangle. You have a right angle triangle, and basically you can calculate the hypotenuse of the right angle triangle to find out the displacement. Now you have to give the size of the displacement first. So we have a right angle triangle. We know this is the formula: c square is equals to a square plus b square, where c is your hypotenuse. So here's what you are going to do. This side is 5 plus 5 plus 5, so this is 15, and this is 1 2 3 4 5 6 7 8 9 10. So this side is 50. So we have 50 square plus 15 square, and you take the under root of that, 2725, and that will give you the resultant displacement, which is 52.2 kilometers. But you have to be careful because they're saying that use the figure 9.1. So basically just show them that you're using the scale and give the basically draw something on the diagram so that they know what you're calculating as your displacement. So I label this line as my displacement. Now what I have to do is also give I also have to give the direction of the displacement, and the direction of the displacement, if you compare it with this thing here, this is north and this is east, so our displacement is somewhat in this direction. So we can say our direction is northeast. Your direction is northeast. You can go a step further and you can also calculate this angle, and this angle can be calculated by, for example, tan inverse 15 upon 50, and that angle would be, but I don't think that would be necessary. Just saying northeast would be enough. Still go ahead and let's calculate the angle, and we'll get it as 16.7 degrees. Now you can also measure it with your protractor, or you can just calculate it like this. Okay, state how distance differs from displacement. So distance is a scalar, displacement is a vector. So distance does not have direction, while displacement has both direction and magnitude. Distance is a scalar, only has magnitude, or you can say size. Displacement, on the other hand, is a vector, has both magnitude and direction. In some parts of the journey, the car is traveling at a constant speed, but is also accelerating. Explain how is this possible. Now, by the definition of acceleration, we know that it is the rate of change of speed. And if the speed is not changing, if the speed is constant, then how is it accelerating? Well, acceleration can take place in two ways. Either your speed is changing or your direction is changing. And if you look at the diagram carefully, the car is not traveling in a straight line. So the car is changing direction. The car is changing direction. Hence, it is accelerating, because acceleration is basically not the rate of change of speed, it is the rate of change of velocity. And velocity, since it is a vector, you have to take into account the speed and the direction, both of those things. Moving on to the next part. At town B, the car makes an emergency stop. The total stopping distance of the car is the thinking distance added to the braking distance. Okay, describe what is meant by thinking distance. So the driver looks at something and he applies the brakes, but during the time when he saw the stop, saw the emergency stop, and the time when he applied the brake, there is a small time period, and during that time period, obviously his car is not stopped. It's going to travel some distance. That is why that distance covered by the driver during that time period is going to be his thinking distance. So it's the distance. The first thing is the distance. Many of you will make the mistake of writing that is the time between applying the brakes and looking at the emergency stop, but no, it's the distance. It's the distance covered by the car between the time the driver sees the stop and applies the brake. Okay, next part. The brakes on the car work badly, so they are not working properly, and this increases the braking distance. State 2 other factors that increase the braking distance. So what you need to consider is which kind of force is basically going to affect the braking distance. The braking distance is always affected by the force of friction, and friction can be affected by many things. It can be because the brakes are working badly, which they have already mentioned, but they want us to state 2 other factors. So one of them could be the tires are worn out. The tires are worn out. They are not in the best condition. They cannot grip the ground very well. So there is less friction due to the tire. The other thing is that the ground, or you can say the road, is wet. This will also decrease the distance. Anything that will decrease the friction is going to increase the braking distance. Okay, the mass of the car in the driver is 1200 kg. Just before the brakes are applied, the speed of the car is 30. So before the brakes are applied, the car is traveling at a speed of 30. Calculate the kinetic energy of the car just before the brakes are applied. Now kinetic energy is pretty straightforward. It's half mv square. You don't really have to do anything, just use the formula. Mass is 12. You don't even have to convert the units, just straight away use the formula. Now you're wondering, why do they have 3 marks for this? This can happen in section B many times, where the question is very simple and apparently it has more marks than you would expect for it. So mostly this kind of question can also have 1 marks only. So that's just answer. The answer will carry 1 mark, and if you make any mistake you will lose that mark. But in section B sometimes they are going to award more marks for a question which is fairly simple enough. So what you can do to make sure you don't lose any of those marks is mention your formula first. So you notice how I've written the formula first, and then I've mentioned my calculations. And you should make this a habit of mentioning the formula first always, even if the marks are more or less, it doesn't matter, because that way, even if you don't substitute the right values or you don't get the right answer, at least the examiner knows your concept was right, and there is a chance that you might get the credit for one of the steps in the questions. Okay, so this is going to be 5400 so 540000 joules. Don't forget the units. The braking force that stops the car is 1800 Newton. That's the braking force. Calculate the deceleration of the car. Okay, so remember, this is your formula, F is equals to ma, but this is the resultant force. Now the interesting thing here is, if the car is traveling forward, if this is your car and it's traveling in this direction, the only force which is acting on it is the brakes, is the force of the brakes, which is the friction. There is no force due to the engine moving the car forward because the driver is applying the brake, so his foot is off the accelerator. The only force acting on the car is the braking force, and which is 1800. So your resultant force is going to be 1800. We know the mass. All we need to do is calculate the acceleration, which is going to be 1.5. So you mention your deceleration or your acceleration, you can say 1.5 meters per second square. You don't have to include the negative sign, doesn't matter. Explain why the temperature of the brakes increase during braking. So friction causes the brakes to heat up as they gain thermal energy. So whenever there is friction between two objects, it's definitely going to result in some form of heat, and that's what is happening here. So this was a very straightforward and simple question, really easy. Should be able to get full marks in this one. Okay, question number 10. Figure 10.1 is a diagram of a soldering iron. So solder is basically an equipment which is used to join the two pieces of metal together. So what they do is there's a heating element which heats this part, and then you bring in a wire from somewhere, which that wire is called the solder and silver in color. So what you do is, so if I want to join this object with this object, what I'm going to do is going to bring the wire close to this heating element, touch it with a metal tip, and this wire is going to melt. And when it's going to melt, it's going to fill the space between the two objects, and then it's going to solidify again, and the two objects are going to be joined together. So that's what a soldering iron does. So solder is a mixture of metal used to make a permanent contact between electrical wires. The heating elements raises the temperature of the metal tip. The solder is placed against the tip, the solder melts over the wire to be joined, the solder cools, it solidifies, and a permanent connection is made. Just what I've explained here. The working temperature of the metal tip is 380 degrees. So the metal tip, when it's working properly, works at this temperature. The boxes in figure 10.2 show two materials and some different melting points. Okay, so one of the material is metal tip of the metal of the metal tip, and the other is the solder itself. On figure 10.2, draw a line for the metal of the metal tip and a line to a suitable melting point for each. Okay, now you don't want the metal tip to melt itself, right? The metal tip should stay solid when it's working, because the only job for metal tip is to heat the soldering iron itself. So it's going to heat up, but you don't want the metal tip to melt itself. So ideally its temperature should be much higher than 380 degrees, because when it's working it is at 380 degree, it needs to stay solid. So the metal tip should be the 1000 degrees Celsius. There is no other option here. But the solder obviously needs to melt, right? So what we want is the solder to melt and then quickly solidify again as well. So a good idea is to have the solder's melting point as close to the working temperature of the metal tip as possible, so that when it when it is melted, it comes back to be a solid again. So the thing is, you can't choose 380. Why not? Because if the metal tip is at 380 degrees, some of the energy is going to be lost to the surroundings as well, and the solder will just start to melt at 380 degrees. So what will happen is, you try to melt it and it probably start going to melt, but it's going to take a long while and it's going to melt very slowly if it is exactly at its melting temperature. So in order for the solder to melt quickly, it should have a temperature which is well below 380 degrees, but also it should not be very close to the room temperature, because otherwise it's not going to solidify again. So 200 degrees should be the melting temperature for the solder iron, so that with the metal tip it is melted, but as it melts and drops onto the metal wires, it reaches the room temperature and then quickly solidifies again. So 200 degrees isn't the right answer. The others does not make sense, because 20 degrees Celsius is around room temperature. The solder is just going to be a liquid at room temperature, and that's what we don't want. We want it to be a solid. Okay, the heating element is rated at 24 volts and 3.3 amperes. So whenever there is a rating given for any component, any electrical component, they're saying that is the working requirements of that particular element. So for a cell, basically they'll give you the EMF. For a resistor, they will give you the resistance. For a lamp or heating element like this, they will sometime give you the power rating in watts, or sometime they will give you the voltage at which it's going to work and the current. And even if you look at any electrical appliances around your house, you're always going to see these two things, one or the other, or the watts on the appliance. So heating element is switched on, the temperature of the metal tip rises from 20 to 320 in first 10 seconds. Calculate the electrical energy supplied to the heater in the first 10 seconds. Now we know that if you know the current, you can calculate the power of the heater, and that would be 24 multiplied by 3.3, and that will give you 79.2 watts. But this is not the answer. This is just one step. What you need to calculate is energy, and energy is power multiplied by time, because power is just the energy being produced in 1 second. You want the energy to be produced in the whole of 10 seconds. So I have my energy per second, which is power, multiplied by 10 seconds, and that will give me the answer for my energy in joules. So that would be 792 joules. Alright, the metal tip is made of copper. So they have given you the substance and has a mass of 2.3 grams. Specific heat capacity of the copper is also given. That is joules per grams per degree Celsius. Calculate the thermal energy gained by the metal tip in the first 10 seconds. Okay, so the thing is, the thermal energy gained by the metal tip is going to come from the electrical energy of the circuit, obviously, but not all of it is going to go there. So we are not going to just write this 792 energy here. That's not happening, because not all of the energy is going to convert into thermal energy of the metal tip. Some of that might be wasted. So we need to use the other formula here. We need to use the specific heat capacity formula, which is this: Q is equals to mc delta T, where m is the mass of the object, c is the specific heat capacity, and delta T is the change in temperature. And we have been given all, and Q is the thermal energy gained by the object. So we are given all these quantities. I've written the formula and we can simply calculate it. So mass is in 2.3 grams, and since this is given in per gram per centiliters, and this is also given in grams, so you don't really need to convert the mass into anything. Specific heat capacity is 0.39, and the temperature change is, as given in the question above, 320 minus 20. So there is a total temperature change of 300 degrees Celsius here, and we're going to calculate this: 2.3 times 0.39 times 320 minus 20, and that will give me the energy of 269.1 joules. I'm going to write it as 269 only, because I don't want to write 4 significant figures in the answer. Just 3 significant figures are enough. Now the next part says, describe in terms of free electrons the process by which heat transfers through the metal tips. So we know conduction is the way in which energy is being transferred, right? But you have to describe the whole process in terms of free electrons and not in terms of the molecules. In most of the material, it's just the molecules that are vibrating, and then their neighboring molecules also start to vibrate, and the energy is transferred that way. But in metals, they have free electrons as well. So the free electrons are going to gain energy, they are going to move at high speeds, and then they are going to strike the particles of the metal, and then they are going to gain energy, which is how the heat is transferred through the metal tip. So you say free electrons move at high speed when metal is heated and strike the particles in their path. The particles vibrate due to this and gain kinetic energy due to which heat is transferred through the metal. So you heat one end of the metal, you apply the heat here, and the energy is going to go from this point to that point because of free electrons. Heat is lost from the metal tip by convection in the air. So explain how convection occurs. Now if you look at the diagram carefully, if I bring the wire close, this is the soldered wire, what happens is not all of the heat is going to be transferred. Some of the heat is going to go to the surrounding air, and that is happening because of convection. So how does convection take place? The surrounding air obviously is going to get heated, and that heated air expands and its density decreases, and when the density of air decreases, it rises. So that's what is happening here. So hot air rises and then cold air comes down, and there are convection currents forming due to which the heat is moving away from the metal. So air around the metal expands when heated. Its density decreases when it expands, so it rises, and cold air above it takes its place. So convection currents are set up. On convection, in these convection currents, the hot air is always going away from the metal, so the surroundings are getting heated. So this is your metal, this is the hot air. The hot air rises and the cold air comes and takes its place. So there is a convection current, a cycle that has been set up around the metal, due to which energy is being taken away from the metal. The temperature of the metal tip is measured with a thermocouple thermometer. In the space below, draw a diagram for a thermocouple marked with letter H, the part of the thermometer that is placed on the metal tip. So the thermocouple thermometer is basically made up of two wires. So what you need is two wires. This is one wire and this is the other wire, and they are joined at two different junctions, but one of the wires needs to have a voltmeter or millivoltmeter across it. So I have two wires and I have two junctions. This is my thermocouple thermometer. The diagram is complete. I have two different wires, wire 1 and wire 2, and across one of the wires I have a voltmeter connected. So we have two junctions. This is junction 1 and this is junction 2, And they're saying draw a label diagram, mark with letter H the part of the thermocouple that is placed on the metal tip. So one of the junctions need to be in melting ice. Why? Because you want one of the junctions to be cold at 0 degrees Celsius. And why 0? Because you want a fixed known temperature at one of the junctions. This is how every thermometer works. You need fixed temperatures to work with thermometers. So this should be at 0 degrees Celsius, and this is the junction that will be touched against the metal or any object for which you have to measure the temperature. So state 2 reason why thermocouple thermometer is suitable for measuring how the temperature of the metal tip varies during the first 10 seconds. Okay, so first thing is thermocouples can measure very high temperatures. That's simple enough. They are robust, they are made of metal, and they don't get destroyed easily compared to a clinical thermometer, which can only measure temperatures around the temperatures which are at room temperature or the temperature of our bodies. So if it goes above, for example, 37 degrees or 40 degrees Celsius, your mercury thermometer will simply explode. The mercury doesn't have any more space to expand. Or even a laboratory thermometer can only rise to 110 degrees Celsius, for example, and not more than that. So your thermocouple thermometer is suitable because it can measure very high temperatures. And remember, our metal tip was as hot as 380 degrees Celsius. So we need a thermocouple thermometer. Very high temperatures. The other thing is it's very responsive. And responsive, by responsive I mean it reacts quickly. As the temperature reading changes, the voltmeter is quickly going to change its reading as well, and you can quickly see the change. If the temperature is changing very quickly, you can actually see it on the voltmeter. What happens with see, you have a very short time to measure the temperature. It's only first 10 seconds. So you want to be able to see the changes in temperature. If you remember in your labs or wherever doing any experiment with a thermometer, you know it takes a laboratory thermometer some time to register the change in temperatures. It rises, the column in the thermometer rises and falls very slowly, but that's not the case with thermocouple thermometer. It's very responsive. It can register or you can say rapid changes in temperature. So this is one more advantage. There are other advantages of thermocouple thermometers compared to laboratory thermometers, but these two are enough for now. So we are done with 2 questions, and this will be the last question. So this will be the last question of this paper. So let's begin. So on to question number 11 now. Stars are formed inside a cloud of gas and dust in space. When stars are formed, the cloud becomes first smaller as it collapses. So why is the cloud becoming smaller and smaller? Well, because the cloud is made up of lots of particles of hydrogen and space dust. What happens is there is lots of mass, and due to lots of mass, all of it is getting attracted towards the center of the cloud. Whenever we have a lot of mass, the mass is just going to attract each other. So this causes the cloud to collapse. So the main reason here is gravity. The force of gravity is basically causing the cloud to collapse. State 2 conditions which are required for fusion to occur. So fusion can only occur when temperature is very high, high temperature. You need to have a lot of mass or very high density. Because only when there is lots of mass and lots of density is the gravity going to become strong enough for the star to collapse. There can be other reasons as well. There can be other points, high pressure. So anything that will help the nuclei to come together easily. So you can write any two of the three above. Now when a large star explodes, a nuclei of heavy elements are formed. So what happens is, one such nuclei is uranium-235. Remember this 235 written when the whole nucleus is named without any symbols, and it's just written the name in complete words, and then there is a dash and the number written. So that number 235 is always the mass number. But they have written it in both forms, so we can see clearly the symbol as well. State the name and the number of each type of particle found in one nucleus of uranium-235. So we can see this is the proton numbers. So the name of the particle can be proton. Inside the nucleus you only have protons and neutrons. This is very clear, so that will give you 1 mark for the names. Now how many protons are there? The proton number is 92, and the number of neutrons can always be found by subtracting the mass number with protons, and that will give you 235 minus 92 will give you 143. So there are 143 neutrons. State one feature that is the same for all nuclei of the isotopes of uranium. Now isotopes by definition are basically nuclei of the same element. So same element means that they have the same number of protons. Their number of neutrons are different. So one feature that is same is the number of protons. A nucleus of uranium-235 in a nuclear reactor can undergo nuclear fission. Describe the process of fission. In very short words, fission is just a splitting up of a nucleus into smaller nuclei. But in a nuclear reactor specifically, what is done is you have a uranium nuclei and you strike it with a slow moving neutron, and that makes the uranium nuclei unstable, and then it explodes into 2 smaller nuclei and 3 more neutrons. So that's what you have to say. Uranium nucleus is struck by a neutron which makes it unstable, and it splits into 2 smaller nuclei. You don't need to remember the names of those smaller nuclei, and 3 more neutrons. Even if you write an answer till here, that would be enough, but still 3 more neutrons. So state one difference between the nuclear fission and fusion. So the main difference is in their definition. Fusion is coming together. Fusion is coming together of lighter nuclei to form heavy nucleus, and fission is the exact opposite. Obviously now I'm just trying to save time here, but you can write the complete thing. That is a heavier nuclei basically splits into 2 smaller nuclei, and that would be fission. So the nucleus of uranium-235 is not stable. Obviously then it will go through radioactive decay, and here it's alpha particle and a thorium nucleus which is being formed. So they're saying complete the nuclear equation below. So if you remember, I will start with alpha, because alpha particle is, if you know, the symbol of alpha particle is this. It is a helium nucleus which has 2 protons and 2 neutrons, so its mass number is going to be 4. Now all that is left to do is just balance the equation, or you can just simply remember during alpha decay the mass number decreases by 4 and the proton number decreases by 2, but just balance the equation. Here we have 92 and here we have 2, So we can just do it like this: 92 is equals to x plus 2. So x should be 90. That would give me 90. And for the top one, I can make an equation: 235 is equals to y plus 4. So y should be 231. That's it. The Giger and Marsden carried out an experiment to investigate the scattering of alpha particles, and there's a diagram of their experiment is shown below. So we have a radioactive source from which alpha particles are being emitted. Then we have a very thin gold foil, and then all around the apparatus we have a fluorescent screen. So when the particles, alpha particles, are charged, when they hit the screen lights up, bright flashes are seen, and that's how you can see if the alpha particles are being scattered or they are going straight through the screen. So on figure 1.1, mark with the letter P where most flashes occur on the screen. So we know from this experiment that most of the particles are going to pass straight through. So if they pass straight through, this is the point where you should see most of the flashes. Describe what is seen on other parts of the screen. So according to this experiment, some of the particles, very few particles, are deflected by less than 90 degrees. So some are going to go in this direction and this direction, and even fewer than that, some of the particles are going to deflect more than 90 degrees and come back and hit the back side of the screen. So what you're going to say is simply fewer flashes on the sides. I mean, this is enough. You don't need to write more, because there's less particles being deflected, so, and most of them pass straight through. So apart from the center, you're going to see very fewer flashes around that point P. State two conclusions about the gold atoms that resulted from this experiment. So the two conclusions were that this is your atom, and in the center it has a nucleus. How they came to know that there is a nucleus in the center was because the alpha particles are passing like this. What happens is, the only reason particles are getting deflected like this, or if they are deflected in the other direction, is because the center of the nucleus or the center of the atom is positively charged. So the center of the atom is positive. That was the first conclusion, because there is no other way the particles wouldn't have passed straight through. But the other conclusion was that because all of the alpha particles are passing straight through the atoms, it's pretty clear that they're not hitting anything. So if they're not hitting anything, it means that most of the atom is basically empty space. Or you can say that the nucleus of the atom is very small. So these are the two conclusions, and I think we are done with the paper. I'll see you in the next one. Thank you.